Right, so welcome to STAT 313, Lecture 16. So today we'll be discussing a new topic, which is called the sequential probability ratio test. This is used in practice in many areas. So I thought it's an important topic which should be included in this course. So we'll be discussing that. So for those who are following the textbook, it's the chapter 8.4, so the fourth section of the chapter 8 in the textbook. Okay. So let's get started. Okay, so this is called the sequential probability ratio test. Now, whatever we have done so far in this course, so so far, when we considered a sample, say we have, say, x1, x2, xn, it's a random sample of a fixed size n. Okay. So this number n we don't change. So we draw a sample of size n. So that is always the first step that we do. Okay. And then we assume that um, they are this sample are from a distribution that has PDF or PMF f of x theta, where this theta is unknown. Theta equals to theta prime or maybe theta double prime. So these two are known number. What we don't know is which one is theta. Okay, it can be theta prime or it can be theta double prime. Okay, so once again, so far when we want to test it, so we considered the log likelihood function, and then step one, we find the log likelihood function theta, and then step two, we construct some ratio, say L of theta prime over L of theta double prime, and based on that, if it's less than k, we develop this procedure. Okay. So this k is positive. So in this case, so if we can find a region like that, if this holds, then H0, which is theta equals theta prime, is rejected against H1, which is theta equals to theta prime, theta double prime. So this is by the last classes. This is a best test of H0 testing against H1. Okay, so that is something we have been dealing with in the last few lectures. So the best test and everything. Okay. Now the most crucial part is here we assume that this n is fixed. Okay. In this section, we'll try to make this assumption relaxed. And what we'll be doing is we'll be supposing that the sample size n will not be fixed in advance. Okay? So in this section, we consider the case when the sample size n um, is not fixed in advance. Okay. So that means it will be a variable, like a variable size for the sample. Okay. So in fact, we'll be assuming that, assume that the sample size is a random variable. So n is a random variable which is taking the values 1, 2, 3, etc. Now, so how do you conduct the test there? So basically, your sample size is changing. So all these previous discussions are not really valid, because all these discussions, so there's everything. So here, based on fixed n. So whatever we write here, fixed values of n. Okay. Now, we can do the same thing. I mean, if we want to conduct a test for a fixed n, so we don't mention n here. So, but if we really want to show the dependence of this log likelihood function on those xn's, so then we'll put an n. Okay, so new notation for this section, new notation, or little change notation will be denoting L of theta, and then I'll write n. Okay, which is really f of x1 theta, f of x2 theta, all the way up to f of xn theta. Okay. So I mean, basically it takes care of two things. One is the parameter value theta, and other one is the sample size n. All right, so let's see what we do with that. So now, new procedure for testing the null hypothesis H0, which is theta equals to theta prime, against, so that's a simple hypothesis, against another simple hypothesis, H1 is theta equals to theta double prime. So let's discuss this new procedure. Okay. First of all, set K0 and K1 to positive constants and constants with K0 is strictly smaller than K1. So K0 is here, K1 is here. Later on, we'll see how these constants are chosen, but for now, we just assume that they are some positive constant. Okay, so that's all for our case. Just two positive constants. Now, observe the independent outcomes x1, x2, x3, etc. in a sequence So we observe the outcomes in a sequence, okay? So such as, say, this is taking the value x, little x1, x2, x3, etc. So these are the values. Little x1 is a value of big x1, little x2 is a value of big x2, little x3 is a value of big x3, and so on. So we are observing these values. And compute. So now we'll be computing the log likelihood function. So now let's go back to this notation. So remember the old test. So the old test was this with respect to the fixed n, right? But I'll be considering bunch of tests. So I'll be considering a new test where this quantity will be dependent on n. So I'll be writing maybe the first one. Let's compute theta prime over theta prime 1. So it's n equals to 1 over L of theta double prime 1. By the way, if this number is less than a k, then that would be the best test for testing the hypothesis based on only one sample. Okay. Now here we have multiple samples. So here we compute this one, and then we'll compute maybe the next one with n equals to 2. Then maybe the third one, 3. All these quantities are same as before. Like here, look at these quantities. We are testing theta equals to theta prime against theta equals to theta double prime. So this is the quantities we're going. So let's consider or let's compute all these quantities. What's the difference between the classical one and this one? So here, based on n, we are changing this. Now here's the deal. The hypothesis H0, which is theta equals theta prime, which is used against H1, which is theta equals theta double prime, is rejected. So that is H1 is accepted when, if and only if the following condition holds. There is, let me just write it in blue, there is a positive integer n, so that let's write xn vector as x1, x2, xn. Okay, by the way, what are this? These are, so I already wrote the sequence that we are observing. So sequences are coming, right? So as soon as you're performing an experiment, you're getting some x1, x2, x3, everything you're getting. Now I'm observing it. So I mean, and by xn, this vector xn, I mean the first n terms of the sequence. Okay. This is observable, right? So correspondingly, I can compute all these quotients corresponding to each and every. So for example, if this n is now fixed, so if this big N is given, then I can just compute, say, L of theta prime comma n over L of theta double prime comma n, right? Now, when do we reject? So this is rejected if there is a positive integer n, so that this belong to the set and then I'll write the set. P sub n, it will be a little notational, but it's not really very hard to understand. Xn, such that if you don't like this notation, let me just write it as x1, x2, xn, such that K0, remember we set up this K0 and K1 to start when we started off this procedure. So this K0 less than L of theta prime of J over L of theta double prime J less than K1 for every J until the penultimate point of the sequence. So it's x of n minus 1. So up to this one, when we observe, this should hold. So J from 1 to all the way up to n minus 1. And L of theta prime n for the nth one. So up to after n minus 1, L of theta prime comma n, L of theta double prime comma n, it's bigger than K1. Sorry, it's less than equal to, sorry, K0. This is what we call the set. And so that means, so if x1, x2, xn, which another notation is xn bar. So this is another notation we used is really xn bar. So if this in, and the notation is belongs to Cn, then we reject H0 and accept H1. Okay. That's the first condition. So this is our critical region. So look at the procedure. So now we are making it explicitly dependent on those n trials, right? So so we are not making it explicitly dependent on n trials. So what we are doing is we are conducting the experiment and we are getting numbers, right? So as soon, we are computing the numbers. So they are between, so K0 is a fixed value, K1 is a fixed value. So as long as they are between these two, we are fine. But as soon as this coefficient, this quotient, it hits the lower point, the lower bound K0, then we say that so we are in the critical region, and then we'll be rejecting the null hypothesis and we'll be accepting the H1. So in this way, we can make it dependent on certain n. Okay. So let me just make it another, or let me just write another one, and then I'll be making another comment, which is useful. Okay. What is the alternative? Like, what is the other way of when can we say that, well, we accept H0? So this is the procedure to reject H0. Now, what is the procedure to accept H0? So on the other hand, the hypothesis H0, which is theta equals to theta prime, is accepted. So that is H1, which is theta equals to theta double prime, is rejected. If and only if. So the previous one was for rejection, and this is for acceptance for H0. If and only if there is a positive integer n, so that xn, which is x1, x2, xn minus 1, and xn, belong to the set B sub n, which is something like x1, x2, xn, such that K0 up to n minus 1, it's just the same as before. K1 for j equal to 1 to n minus 1. And then L of theta prime n over L of theta double prime n is bigger than equal to K0. So is bigger than equal to K1. So as soon as it hits the upper limit and it goes past that, then we say that we are taking our null hypothesis to be true. So we are accepting it. Okay. So here is a brief schematic. So that's pretty much it. Okay. So here is a schematic diagram. So here is my K0 and here is my K1, and you compute all those quantities, right? So basically you compute L of theta prime with some J, L of theta double prime over J, and you let this J run. As soon as you have this quotient somewhere here, the left endpoint, look at that. So if it is going, so its value is less than or equal to the left endpoint. So then we reject H0 and accept H1. But as soon as this value is hitting K1, we accept H0 and reject H1. So that is the schematic. So if I have an interval, so now you may wonder how we construct this K0 and K1. We'll come to that later. But so this is pretty much it. So you compute this quotient for every J. Now, if for some J, you get this number at one of this in the left endpoint, then you reject H0. If for one of these J's, you get it for the right endpoint, then you accept H0. Okay. So that is pretty much it. So here is the scheme. So we stop the observations. What do you mean by stop? Because every time we are getting an observation, so maybe xj, we are computing this, right? And then if it's in between these two, then we go to the next one. If it's again between these two, we go to the next one. So we only stop as soon as it hits one of these two endpoints. So we stop the observations in one of the two ways. Number one, we reject H0 as soon as we have seen right here. So it hits K0 or it becomes less than that. Remember, this is not a continuous number. So for every J, it can be like there can be various values. So when you go past this, so if this number goes past this, so that means it can be either hitting this K0 or it can be less than that. Is less than equal to K0. And then we accept H0 as soon as you get an observation. Sorry, I didn't write the complete thing here. It's L of theta double prime. Let's write it N for the nth case. Theta double prime N. And here, theta prime N, L of theta double prime N bigger than equal to K. So that means so N is the stopping time of the process. So if we are like we're stopping the process at the time N. So as soon as we get an observation which is satisfying one of these two properties, then we say we're stopping there. All right. So this is pretty much it. So this is the sequential test. So now we'll be devoting times in finding these two constants, but essentially this is a test. Okay. This is called Wald's sequential probability ratio test. Okay. Now you see that basically it's giving you a way, um, like if this ratio is more than or less than something, then you reject or accept a null hypothesis, right? In other words, when this ratio is in between K0 and K1, you don't do anything, right? So essentially, another form of this one is, I mean, it's between two numbers which are functions of n. Okay, an equivalent form. So C0 of n is less than U of x1, x2, xn is less than C1 of n, where this U of x1, x2, xn is a statistic depending on the n samples, and this C0 n and C1 n, they depend on constants. First of all, K0 and K1 that we pre-assign, and then we can have theta prime, it can depend on theta prime, and on n. So, and the decision rule in this case, the observation stream, that means remember that we have x1, x2, x3, all these observations are coming. So this observation stream is stopped and a decision is reached as soon as either this value of the statistic is less than equal to C0n, or the value of the statistic is more than or equal to C1n, right? Okay, so that is the deal with the sequential testing. And that's pretty much it. And as I mentioned, that now we'll be spending most of our time in understanding this test and how do you characterize the C0, how do you characterize C1, and all those things. But essentially, what we have done here is the summary of the entire thing. So example. So let's start with an example. Okay. So X has the probability mass function, which is given by f of x theta, which is equal to theta to the x, 1 minus theta to the 1 minus x, and the values of little x can be 0 or 1, and 0 elsewhere. Okay. So let us consider h0, which is theta equals to, say, 1/3 against, we're testing the alternative hypothesis. Sorry, we're testing null hypothesis, theta equals to 1/3 against theta equals to 2/3. Okay. Use a sequential probability ratio test to reach the decision. Okay, so here is a tentative solution? Well, for all this, first of all, what do you have to compute? So we have to compute, say, let's see. So if I have L of theta n, what does it mean? So it's for first n, so there are n samples, and the unknown is theta, right? So therefore, what is the quantity here? So basically, it's theta to the, well, theta to the xi 1 minus theta to the 1 minus xi, and then we multiply this from I from 1 to n. Why n? Because there are n samples. Okay. So this is really, I have, sorry, theta to the summation of xi, and then 1 minus theta to the summation 1 minus xi. I'll just simplify it one step. So it becomes theta to the summation I from 1 to n xi. And summation 1 is really n, right? So it's n minus summation I from 1 to n xi. So that is the likelihood function in this case. Now, let's go back to the test. So what do you test? So we'll be computing this quantity, right? It's the theta prime over n over theta double prime over n. So let's do it for certain n. So now, then L of, say, theta prime is 1/3. So that is my theta prime of n over L of 2/3 n. So this is really theta double prime. So that is going to be, first one is 1/3 to the summation of I from 1 to n xi. And then we have 1 minus 1/3, that is 2/3 to the power n minus I from 1 to n xi. So that's the numerator. And the denominator is 2/3 summation xi, I from 1 to n, and then 1/3 n minus summation I from 1 to n xi. Okay. If you simplify this, it'll be, let's see, it's 2 to the n minus 2 summation I from 1 to n xi. Okay. So that's this ratio. Now, so what we want is initially, so for the first few observations, so if this ratio is between K1 and K2, sorry, K0, then we don't make any decision, right? So for those n, so you have this quantity between K0 and K1 for some fixed K0 and K1, we don't make any decision. So what does it mean in this case? So it's 2 to the n minus 2 summation I from 1 to n xi less than K1, right? Take a log base 2, so that because it's 2 to the power of something. So take a log base 2. So we have log base 2. All these are positive numbers, right? So, and this is n minus 2 summation I from 1 to n xi less than log base 2 k1. Okay. So that means, okay, so let's consider this two separately. Um, if this quantity reaches this one, let's look at the picture. So when it reaches this one, we reject the null hypothesis, okay? So reject H0 if log of 2, if n minus 2 I from 1 to n xi is less than equal to log of 2 k0. Okay. So in other words, this can be same as if I just solve for this quantity. So it's n minus log 2k0 over 2 I from 1 to n xi. So if this summation of this xi is bigger than this quantity, then we reject the null hypothesis, right? Let's call this one, say, okay, I'll call this one something pretty soon, but let's continue doing this. And accept H0 provided this thing here, I from 1 to n xi is more than that, right? So log 2 of k1. So if I again solve for this one, so it's n minus log 2 of k1 over 2 is bigger than I from 1 to n xi. So here's the deal. So we are observing the sample, and there are these two numbers which are prefixed, right? So I mean, this is one value dependent on n, because n is here. Now we compute this one. As soon as you're getting this bigger than that, you're done. So you compute the sum. If it's more than this one, more than or equal to this one, you're done, and you reject the H0. And if this number is here, if this inequality is satisfied, then you're done at that n, and you accept H0. Okay, so let's give it a name. So for instance, so this is, so let's call it C1n. You'll see why this, I call it C1 pretty soon, and let's call this C0n. Okay, so here it's easy to see from here. This inequality, I can write this as n minus log of 2k1 over 2 is less than I from 1 to n xi is less than n minus log of k0 base 2 over 2. Now this is what we called right here k0. So it's c1n, and this is what we call c0n. So that means when this sum is when the sum of the samples is between this C0 and C1, we don't make any decision. As soon as the sum is touching some boundary, then we are making a decision. But please note that whenever the sum actually, so what is happening is, if this ideally, like when we started doing this test, when we are just a simple ratio, then we reject the null hypothesis as soon as it's less than or equal to k0, right? So if it's a left endpoint, we are rejecting. But here, what's happening is we are not really computing a simple a likelihood function. So it's basically a statistic based on likelihood function. So then what is happening is, if it's passing, if it's passing this one, this lower one, so then we are rejecting null hypothesis. Okay. And on the other hand, here we are accepting the null hypothesis. Sorry, what I mean is, I think I made an error. So this C1 is not here. So this is C1. It really appears right here. And this is C0, which really appears here. So it's a little bit flipped, meaning that when this test statistic value is passing this part, the lower bound, we are really accepting H0. In the last picture, remember, it was rejection if it's just the simple likelihood function. But here it's a little bit different, because we are using some versions. I mean, we are not really using the the likelihood function or likelihood ratio. So we are using a function of it. Okay. All right. So here, if I draw a picture, so it will be something like this one. So my C0n is here, my C1n is here, and this is the function u of x1, x2, xn, the statistic, which is I from 1 to n xi. What happens when this quantity goes to this one, the C01? And look at this. So it's um, so if the statistic value is less than or equal to C0, then we accept H0, versus if the statistic value is more than or equal to C1, then we reject H0, okay, based on this statistic. Okay. So it always depends on the statistic. In the last picture, it's different. Remember, look at the last picture. It was reject H0 accelerated, but here the statistic was different, right? So here we are considering the sum of xi's. Here it was something different. So that is the reason. Okay. Now let's do another example. But before doing that, doing another example, there are some important issues. For instance, when we are studying this test, the test is, I'm trying to find the test. It's right here. Okay. So we constructed all these ratios, and then whenever this ratio for certain n, it goes to k0, we reject the h0. Again, go back to the original test. And if this ratio is k1 or more, we accept the null hypothesis, right? What is the guarantee that this number will ever leave this k0 or k1? What if it stays inside this k0 and k1 for eternity? Okay. So that's an automatic question, right? So then we can neither accept the null hypothesis nor reject it, right? Because this number is always between these two. Now, so this is a very good question, but there is no way we can answer this question for this course. So result. What is the probability of the procedure continuing indefinitely? That means we are running a bunch of experiments, but the value is always between k0 and k1. Okay? It's never leaving this loop. So the process. So that means that we have to, every time we are performing the experiment, we are looking for the next one, but the next one is still there, so we cannot do much. Okay. Answer: probability is 0. Okay. We cannot prove this in this course, so it will need some more advanced tools, so we'll be skipping it. But know that at some point of time, this process, so this log likelihood ratio, will leave either the left endpoint or right endpoint. Okay, it cannot stay in between forever. So that is one question. And then, so let's try to understand those two constants. Okay? So let us try to understand. So that was the first important result. And the second one, let's understand K0 and K1. Okay? Because as we have seen that they are predefined and they play a major role for this decision making, right? So whenever this quantity is going to the left-hand point or going here or less, we're rejecting the null hypothesis. Whenever it's here or more, we're accepting the null hypothesis. So the thing is, both of this K0 and K1, so they are very important, making the decision, right? So that's why they are really, really important. Okay. Now for this, I'll be reminding you that this is what we have. Okay. Remember that we have this. I'm copying this one. So we have some C1, which is a critical region for rejecting the null hypothesis. So remember that Cn is given by the x1, x2, xn, such that k0 less than L of theta prime j, L of theta double prime j less than k1, and we have j from 1 to n minus 1, and L of theta prime n, L of theta double prime n is less than k0. So in this case, if x1, x2, xn is in Cn, we reject H0, as we have seen. So that is the first one. And then the other one was Bn, which is the x1, x2, when we accept H0. So it's first part is same as before, L of theta prime j, L of theta double prime j less than k1 for j equals to 1, 2, n minus 1. The only difference is now and L of theta prime n, L of theta double prime n is bigger than k1. And if x1, x2, xn in Bn, we accept H0. Yep. Again, there's nothing new. We already know this. We'll be using this for understanding the K0 and K1. So let's see how. Okay. Let's define alpha. I mean, we have already defined alpha and beta. So what was the alpha? Alpha is the probability of type 1 error. So probability of committing type 1 error. That means probability of, which is really reject H0, such that H0 is true. That is my alpha, right? And beta is the probability of committing type 2 error. And what is that? So this is probability of accept H0 when in fact H1 is true. And remember also we know that 1 minus beta is the power of the test. So we have seen all these things. So it's basically probability of rejecting probability of reject H0 when H1 is true. Okay. All right. Let's see what we want to do with that. I can write based on all these notations. So this alpha, which is hence. So alpha is probability of rejecting the H0 when H0 is true. So now, so that means when can we reject provided? So we are in the set Cn, right? So alpha is Cn L of theta prime, comma n, and then summation n from 1 to infinity. So I just realized that I never defined this notation. So let me just quickly define it. So what it says is, I mean, suppose we have something like this one, say integration, bunch of integrations. So there are n integrations. So we have x1, x2, xn, and we have, say, theta x1, x2, xn, and then this n is fixed, right? By the way, so this we sometimes just we skip this, or we drop this x1, x2, xn. We don't write anything. But if I integrate this in a region with respect to dx1, dx2, dxn over r, okay? So r is a region in the x1, x2, xn plane. So its abbreviation is notation. I'll be simply writing this by integration over r, and then L of theta, or theta comma n. So that's a notation that we'll be using. What does it give me? So it gives me the probability. So this gives me the probability that x1, x2, xn in R when parameter equals theta. So that's what it gives. Okay. So now we are rejecting the null hypothesis provided the values of x1, x2 is in Cn, right? So that's the time we'll reject it. But this n now here, it can be anything. So it can be 1, it can be 2, it can be infinity. So there is no restrictions on n, right? So it's basically n from 1 to infinity. Okay. Similarly, 1 minus beta, which is the power of the test, which is rejecting H0 when H1 is true. So now I can write this as H1 is true and I'm rejecting. So I'm rejecting means it's on Cn, and my H1 is true means my parameter is theta double prime, right? So it's L theta double prime n. And then I'm summing over all such n's. Okay. Now also we know with probability equals to 1, the process terminates. Okay. So 1 minus alpha, so that means either H0 is true or H1 is true for sure, right? So what is 1 minus alpha? So this is the probability of accepting H0 when H0 is true, right? So what is this 1 minus alpha? So it's accepting means I'm in the region Bn. Remember, so we defined all these regions right here. So Bn is the region for which we accept H0. And therefore, this is going to be, and H0 is true, so it's theta prime n, and then summation n from 1 to infinity. So that's 1 minus alpha. And also beta, we're just doing the setup. After that, it will not be that hard. And beta, what is beta? So beta is the probability of accepting H0 when H1 is true. So accepting H0 means it's on Bn, and it's L of theta double prime n, and I sum over n from 1 to infinity. So that's my beta. Okay. That's all the setup. Now, if x1, x2, xn is in Cn, look at Cn. So Cn means this is true, right? Then I can write alpha, which is equal to summation n from 1 to, I'm just using this definition right here. Summation n from 1 to infinity Cn L of theta prime n. Okay. But this L of theta prime of n, when you are in this region Cn, so L of theta prime n would be less than equal to, so if you are in this critical region, then L of theta prime of n is less than k0 times theta double prime n, right? So that's how this Cn is defined. So this is less than equal to n from 1 to infinity Cn k0 L of theta double prime n. So we are using this inequality. This is less than this in Cn. Okay. And then we have seen this, the k0 can be pulled out. So k0 and then summation integral this Cn that we have already defined. And that is right here. It's 1 minus beta, right? So this is nothing but k0, 1 minus beta. Done. So what we found is the following. So hence we must have alpha less than equal to k0, 1 minus beta. So if type 1 error and type 2 errors is specified, then this is the relation that k0 must hold. Or in other words, k0 is bigger than equal to alpha over 1 minus beta. Either of this is fine. Okay. Also, if so this is what we did for Cn, for if x1, x2, xn in Bn. Remember, we can always all we have. So this is I wrote here with probability 1, but I probably didn't explain. So either Bn or Cn is true for some n. Okay, so that means either we'll accept the null hypothesis or we'll reject it at some n, right? So that means if this Cn is true, as then we did this analysis. But if this Bn is true, so for every point Bn, we must have 1 minus alpha, which is equal to, we wrote it before, 1 minus alpha. I'm writing this expression. So it's going to be summation in from 1 to infinity Bn L of theta prime n. Now, on the set Bn, we have again this inequality. So on Bn, it's theta prime is bigger than equal to k1 times L theta double prime n, right? So if I use that relation, so what I have is it's bigger than equal to n from 1 to infinity Bn k1 L of theta double prime n. So here this and this are compared. Bigger than equal to in Bn. If I pull out k1 and if you have the last integral, so that is really speaking, it's beta. Look at the beta value of beta that we derived. So it's right here. So it's right here, beta. So it's really, this is K1 times beta. So that means we must have 1 minus alpha bigger than equal to K1 beta. Another way of understanding this is K1 is less than equal to 1 minus alpha over beta. So the constant, the predetermined constants, alpha and beta, if we instead like the type 1 error and type 2 error, if we just set it at the very beginning, then this K1 and K2 can be set using this form. Okay. So of course, this is provided. So this is provided beta is not equal to 1, and this is provided beta is not equal to 0. So beta cannot be 0 or 1. So this is telling us something about the constants. So let's do little further analysis. Okay? So a little more analysis on K0 and K1. We understand it's upper bound and lower bound given the type 1 and type 2 error. Okay. So the way we'll be dealing with is we'll be considering some type 1 and some type 2 errors are given. So suppose that alpha sub alpha prime and beta prime. So this is the pre-assigned proper fraction of alpha, and this is also the pre-assigned value in fraction. This is also in fraction, meaning it's a number between 0 and 1. Okay, so examples, some examples, it can be say 0.01, it can be 0.05, it can be 0.10, etc. Set my K0. Remember what was K0? So K0 was bigger than equal to this one. So suppose I set this equal to, with this pre-assigned value, so I'll set this equal to alpha prime over 1 minus beta prime. And I set K1 equals to, remember, this K1 got to be less than 1 minus alpha over beta. So it's, let's write this as 1 minus alpha prime over beta prime. So that means I must have, so if alpha equals to the type 1 error probability, actual type 1 error probability, beta equals to type 2 error probability, then K0, which is this one, I must have this K0 bigger than this quantity, right? So that means I have alpha over 1 minus beta is less than equal to alpha prime 1 minus beta prime. So this is from here. And 1 minus alpha prime over beta prime is bigger than 1 minus alpha over beta. Once again, this is coming from right here. Right? So K1 is less than that. We have found it. So this is by 1, 2. So the first one is by 1, and this is by 2. Okay. Now you can simplify this. So basically, the first equation and second equation, if I simplify, the way to do it is let's FOIL it out. So if I cross multiply, all these numbers are positive, right? So this means alpha minus alpha beta prime is less than equal to alpha prime minus alpha prime beta. And we have here beta minus alpha prime beta is less than beta minus alpha beta prime. Sorry, beta prime. If you add these two, then I get, or let's not add this two. So let's subtract these two. Okay, let's add these two. So I have alpha plus beta minus alpha beta prime minus alpha prime beta is less than alpha prime plus beta prime minus alpha prime beta minus alpha beta prime. So you see that this terms cancels. So what we get is alpha plus beta is less than equal to alpha prime plus beta prime. So the problem, so this is what? So this is the probability of two kinds of error. It's our pre-assigned bound. So there is a pre-assigned bound. So if we choose alpha prime and beta prime at the very beginning, then I mean, the probability of two kinds of error combined, it's bounded by this number. Okay. So or also, I mean, I mean, I can even find the bound for instance, let's name this number 3 and name this number 4. So from 3, also from 3, I can write alpha less than 1 minus beta, alpha prime 1 minus beta prime. Now this is a fraction, right? So therefore, this is less than equal, this is strictly less than. Remember, beta cannot be, so this beta cannot be the value 1 or 0. So it's alpha prime 1 minus beta prime. So this is the first relation. The type 1 error is bounded by this one. Similarly, from 4, we can go, so by 4, I mean this one. So 1 minus alpha prime is smaller than or let's flip this. From 4, let's flip it. So beta prime over 1 minus alpha prime is bigger than beta over 1 minus alpha, and then multiply this. So beta is smaller than 1 minus alpha, beta prime, 1 minus alpha prime. So that means beta is less than beta prime, 1 minus alpha prime. So that's another. So this is the bound for the type 2 error. Okay, and the previous one was the bound for type 1 error. Okay. So that is all about how we can compute. So now let's jump into an example. So the rest we can just study some examples. Okay. So let X follows a normal distribution with mean theta and variance 100, where theta is unknown. To find the sequential ratio test for H0, for testing H0, 75 against H1, which is theta equals to 78, such that alpha is approximately equal to 0.1 and beta is also approximately equal to 0.1. So let's do the sequential ratio test. Here is the solution. Or let's not write to find. Okay. So here is the solution. So my alpha value and beta values are given, right? So we know how to, this is the pre-assigned value. So if this is given, I can always take, this K0. So that is the pre-assigned alpha value over 1 minus beta prime, right? So let's solution is K0, set K0 to be the alpha value over 1 minus the beta value, right? So which is about 1 over 9. And set K1 to be 1 minus alpha prime over beta prime. So that means, so let's write this as 1 minus 0.1 over 0.1. Sorry, 0.10. 0.9 over 0.1, which is 9. So these are K0 and K1. Now let's do the hypothesis testing. Okay, so let's compute the likelihood ratio. So compute L of 75n over L of 78n, which is for the numerator, it's e to the minus 1/2 I from 1 to n xi minus 75 over 10 squared. And for the denominator, it's e to the minus 1/2 summation I from 1 to n xi minus 78 over 10 squared. Okay. So if you compute this, it's going to be e to the, I think it's e to the minus 6i from 1 to n xi plus 459 over 200. Yeah. So that's the quantity that you get. Okay. So that implies that if I want this this 1 over 9, which is incidentally K0, and then we have K1, which is 9, I want my this when we not make a decision, so L of 75n, L of 78n, and we are not really making a decision, then it's between these two, right? So it's going to be equal to log of minus 9 is less than, so this is nothing but this quantity is right here. If I take the log, so it's basically minus 6 summation I from 1 to n xi plus 459 over 200 less than log of 9. Log of 1 over 9 is negative log over of 9. So now, basically, if I just simplify the left side, so this part is understood as log of 9 is bigger than 6 of I from 1 to n xi minus 459 over 200. I'm multiplying by the negative sign, so the inequality flips. So if I simplify this, I'll get summation I from 1 to n xi is less than 153 over 2n plus 100 over 3 log 9. So that is for the left inequality. Okay. So that means when we are, so according to the regular test, when this quantity is hitting the left side of the picture, so then remember that we have done this. So we reject the null hypothesis when in this one. So this is when if if this quantity is more than this one, we reject the null hypothesis. So that really means that if summation I from 1 to n xi is bigger than equal to 153 over 2n plus 100 over 3 log 9, we reject h0. Okay. On the other hand, for this one, we get, if I multiply with the negative sign, so I have 6i from 1 to n xi minus 459 over 200 is bigger than log of 9 with a negative sign. So we have, if we simplify this, we get summation of I from 1 to n xi is bigger than 153 over 2n minus 100 over 3 log of 9. Okay. So that means, once again, look at this last picture. So if we are passing this one, we accept the null, right? So that means if summation of I from 1 to n is less than equal to 153 over 2 minus 100 over 3 log 9, we accept h0. Okay. So let's see. So based on this one, at least based on this two, this one, let's call this 1, and this one, let's call this 2. So by 1 and 2, actually the summation of xi, I from 1 to n, is between, it's less than equal to 153 over 2n plus 100 over 3 log of 9, that we are calling as C1 of n. And remember, this C1 of n really appears here. So this is your C1 of n. Okay. And this is bigger than 153 over 2 minus 100 over 3. Sorry, there's an n missing somewhere. 153 n over 2. So this we call C0. So this is really your C0 of n. So this is C0n. This. So there are two ways of understanding this. So basically this quantity, this statistic, they lie between, it lies between C0 and C1, right? C0n and C1n. So consequently, we are rejecting H0 provided that sum of xi is more than C1, right? So that is what here we, so if summation I from 1 to n xi is bigger than C1n, we reject H0. And on the other hand, if summation I from 1 to n xi is less than C0n, we accept H0. So these two are the decision rules. Okay, so the acceptance and rejection of the null hypothesis. Okay. All right, so this is one of the examples that show the importance of this, like whenever you have the preset alpha and beta value, so you can devise a rule this way to compute, say, K0 and K1. And consequently, you can derive your test. Now, let's consider one more example, and that is from the exercise. So this is example. And this is 8.4.2. It goes like this. Let X have a Poisson distribution with mean equals to theta. Find the sequential probability ratio test for testing H0, which is theta equals to 0.02, against H1, which is theta equals to 0.07. Show that the test can be, show that this test can be based upon the statistic summation I from 1 to n xi. If alpha prime equals to 0.20 and beta prime equals to 0.10, find C0n and C1n. Okay. So these are the pre-assigned values which are given. Now, of course, the way we compute the value of K0 and K1, so this is very much similar to what we have done earlier. So solution. First of all, we have to set the two bounds. K0 is alpha prime, 1 minus beta prime, and K1 is 1 minus alpha prime over beta prime. So in our case, this is going to be, so this is really 20 over 90. So it's 2 over 9. And K1 is, it's basically 80.80 over 0.1. So it's 8, right? Okay. Now let's consider the log, so the likelihood function, as we have done in all these previous examples. So in this case, L of, so we are testing for theta equals to 0.02 versus theta equals to 0.7 for the Poisson process, right? So L of theta equals to 0.02 over L of theta equals to 0.07 for the Poisson process. We'll check. So it's basically, by the way, I should also mention n. So for n, because I'm writing n. So it's e to the minus lambda. So for each for every Poisson process, for the case of each one, it's e to the minus 0.02, and then we have n of those. So it's, let's write this way, 0.02, and then 0.02 to the xi over xi factorial. And how many of those? N of those. And for the denominator, we have I from 1 to n, e to the minus 0.07 times 0.07 to the xi over xi factorial. So you see this xi factorials and xi factorials cancel. And then there are basically some of this. So you have product of this one. So it's e to the minus n times 0.02. And here it's e to the minus n times 0.07. So for this term, and here it's 0.02 to the power I from 1 to n xi. And here it's 0.07 to the power of I from 1 to n xi. Okay. So that's the likelihood ratio. I can simplify this further by writing this as, so we want this quantity to be between K0, which is 2 over 9, and K1, which is 8. We want this thing to be in between these two. Now, what is this thing? So you have 2 over 7 to the I from 1 to n xi. And then this is e to the 0.05 times n. So if I take the logarithm, so that's pretty much it, right? So this is the test. Now, if I take the logarithm, I'll have log of 2 over 9 is less than 0.05 n plus summation I from 1 to n xi times log of 2 over 7 less than log of 8. Let's talk about the left side. So we're trying to see that that it's this test can be done for this test statistic. So this statistic xi summation of xi summation of xi. So let's see. So let's try to find the bound. So it's log of 2 over 9 minus 0.05 n is less than log of 2 over 7 summation I from 1 to n xi less than log of 8 minus 0.05 n. So I'm subtracting this from both sides. Now let's look at this number. So this is a negative number, right? 2 over 7 is a fraction less than 1, so this is a negative. So if I divide by that, the inequalities change. So it becomes summation I from 1 to n xi. So if it becomes bigger than log of 8 minus 0.05 n over log of 2 over 7. And this inequality becomes log of 2 over 9, 0.05 n over log of 2 over 7. In other words, so this is something which is the upper limit, which we call C1n, and this is something which is the lower limit we call C0n. And just like before, you can check that just like the last problem, since the inequalities here are flipped also, if summation I from 1 to n xi is bigger than equal to Cn, sorry, C1n, then that is the domain when we reject H0. because this side was, remember, this is for rejecting and this is for accepting. If xi, I from 1 to n xi, if this goes past this one, so that means it becomes smaller than C0n, then we accept H1. Sorry, accept H0. Okay. So that's the case for the Poisson process. So this is how we can consider this for a Poisson process. So that is pretty much it regarding the sequential hypothesis testing. So what we understood is we found a way to sequentially process the data, and then we are creating a decision rule based on our sequential processing. So if the decision rule is always with respect to an interval, so if this number is going below a certain point, then we are having a particular decision rule, and usually it's to reject the H0, but if it goes above the particular value, it's usually to accept the H0, okay? And that is how we have done this here. So this is all about chapter 8 that we want to talk about, and next time we'll be starting chapter 9. So thank you very much.